The motion of objects in space is governed by the universal law of gravity. So let's consider how this works. We have two objects here, object 1 and 2, and that could be two planets or two asteroids or two white dwarfs, black holes, any kind of objects you can imagine. And they are mutually attracted by each other due to gravitation. So we have a gravitational force, and we label this as F, and this is the force on object 1 due to the interaction between the bodies 1 and 2. And here we have a force that's a force on object 2 due to the interaction between objects 1 and 2. And the objects are separated by a distance r, 1, 2. Now we want to derive the universal law of gravitation. How we're going to go about that? Well, Newton figured out a while ago that it is proportional to the masses of objects 1 and 2. So this one has a mass m2 and this one has m1. And it is also proportional to the square of the distance between the two objects. Now we need to do one more consideration and then we can derive this. We need to actually, well, first we need to pick some kind of origin from where we are considering these two objects to be. And this object here goes from the origin to there, and we call this R1. And then we have here R2, which also means that the distance here between object 1 and 2 is R12. And actually we know from vector decomposition that R12 equals R2 minus R1. So just this minus this gives us this distance here. Now, if we want to write down the universal law of gravitation, we also, there's a magnitude component to it, and we also need a direction. And we haven't yet chosen a coordinate system. We could, of course, choose our usual way of placing the I-hat direction in the x coordinate, in the x direction, and the j-hat coordinate in the y direction. But when we deal with the universal law of gravitation, it's actually better to adopt a slightly different coordinate system. Everything in space usually orbits one another, so it's much better to think in a radial direction rather than just normal Cartesian coordinates. And so in this case, we're going to choose an r-hat vector, which gives us the radial direction. And we're going to do this here. So this is going to be our r-hat direction on object 2. And here we have an r-hat direction 2, 1. And we're going to come back to the r-hat unit vectors later. For now, we can just write here quickly down the definition for a unit vector. So our r-hat 1, 2 is, of course, the vector itself, r1, 2, divided over the magnitude of the vector. We can write it like this. And now we can write down the gravitational law. So the force on object, we're going to look at object 2. The force on object 2, due to the interaction between objects 1 and 2, is proportional to the mass of the two objects. We already said that in the beginning, and the square of the distance between the two objects. But what about the direction? The direction here, we were looking at object 2. We placed our r-hat unit vector to point down, but the force is going in the opposite direction, so in the negative r1, 2 hat direction. So we have to add a minus here and then r1, 2 r hat. And as it is the case with most of these laws, there's a proportionality constant. and Newton called this capital G. And G, as we know today from experiment, is 6.67, 10 to the minus 11. And then in terms of units, we have Newton. Force goes in Newton. We have mass. This is kilogram squared. And we have meter squared. So that are the units, and if you plug those in, then the units of the whole equation will work out. So let's quickly consider the force in object 1 to see what's happening over there. So we have F21 equals minus G M1 M2 over R12 squared. And in terms of the unit vector, we now have R21 hat here going. So again, this minus goes with this unit vector, and that one is pointing here in the opposite direction than our force. So that's all good. But what we see from this one here, and actually from our diagram already, that R12 equals minus R21. And so we see from this then that actually Newton's third law, every action has an equal and opposite reaction, is true for this little setup here as well, because the forces are of opposite direction and of equal magnitude. The little prince lives on his asteroid B612, and he really likes to watch the stars. And what he really wishes for is to watch the stars while floating, to have the best possible view and to just immerse himself in the stars. And so the little prince has to think if there is a position in space with respect to other celestial bodies where the gravitational force would just cancel so that he can float. Let's look at that. So there is the planet of the businessman. We're going to give it the mass M1. And there's also the small planet from the lamplighter floating around with mass M2. And we know that gravitational forces act radially. So we can already see here that if we put the asteroid B612 somewhere here, then maybe we find a constellation where gravitational forces cancel. So let's start by placing the little asteroid over here. And what is this body experiencing in terms of gravitational forces? Well, it's going to experience a gravitational force of object 1. So we have object 1 or F1m due to the interaction between object 1, so the business man planet, and our little asteroid here. And then we also, of course, have the same direction here due to the interaction of object 2 and our little asteroid. So that would be F2m. And you can clearly see that if we tally up these forces, they're not going to add to 0. So this is not a good location for the little princess asteroid to be. The same would be true if we put it out here. It will experience those same forces again. What do we have here? 1m and 2m, just going in the opposite direction. But you have guessed it already, we can find a spot here in the middle where one force goes in this direction. So this is F2m. And actually we should give those forces direction. And the other body exerts a force going in the other direction. And so we can see that we now just need to find that exact position here in between these two objects with two different masses, where the little prince can free float while watching the stars. We can say already that if these two masses were the same, it would obviously be in the middle. but because they are not the same, we have to calculate what that distance is. And so we're going to label this distance here x, and we're going to say that the two bodies here are a distance d apart. All right, how are we going to go about this? Well, we have to apply the universal law of gravitation in our F equals ma analysis. Well, before we start with our F equals ma analysis, we actually have to pick a coordinate origin and a unit vector. And so let's place the coordinate origin in here, and let's have I hat go in this direction, and we're going to label this here position A and position B and position C. These are our three options for asteroid placement. And well, let's look at position B. And well, we have the universal law of gravitation between the mass of the object here, and we'll have to describe both components. So first this one, F1m, and then F2m. And if we start with F1m, that goes in the negative I hat direction, so minus gm m1, and the distance is x squared in the I hat direction, and then the other one goes in the plus I hat direction, and we have g m2, and now we have d minus x gives us this portion, d minus x squared, also in the I hat direction. And that needs to add up to 0, because that is what we want, right? We want this to, if it adds up to 0, then we have no gravitational forces acting on the asteroid. So now we need to solve this for x here. And in the first step, we see that actually g and m will fall out here. And then we're left with m1 over x squared minus plus m2 over d minus x squared. And we can write that as m2 x squared minus m1 d minus x squared. And what you see here is that this will turn into a quadratic equation. And if we do a few steps of arithmetic and then write down the general solution to this quadratic equation, we will find this here. X equals 2 dm1 plus minus 2 dm1 squared minus 4 m1 minus m2 m1d squared, and then the square root of that over m1 minus m2, and actually we need 2 of those. So we have this quadratic equation here, well, the solution, and we now need to consider one more thing, namely this equation here is only valid if, where can I write this? Here. If x is between 0 and d, right? If I, in position C, my x is larger than d, which means this, this force here flips sign, and then this would be different. So this plus here refers to x being less than d. And we have to decide which of the two signs here gives us the correct, which fulfills this requirement here. So this simplifies to x equals d m1 plus minus m1, m2, and here we have the square root, and then here we have another bracket over m1 minus m2. And we need to get this term here smaller than 1, or to be smaller than 1, if the x is between 0 and d. And as it turns out, that is indeed true if we use the minus sign here. Let's consider the universal gravitational law a little bit more. Let's consider two objects in space. Let's say this is the sun, and we have the Earth here, or the Earth and the Moon. And of course, they're orbiting each other. So we can pick a coordinate system that goes radially. And so we're going to have an r hat direction here. And we want to call this the r hat direction between objects 1 and 2. What forces are acting on this little moon here? Well, it's the gravitational force going inward. It's the force F12 on object 2 due to the interaction between bodies 1 and 2. For that, we can write down the universal gravitational law. F12 equals minus g, the gravitational constant, m1, m2 over r12 squared. That one is the distance between the two objects, times r12 hat. And the minus goes actually with the unit vector here because the force goes in the opposite direction from our r hat. Let's now consider, here is the Earth again, and we're going to move the moon or a little moon rock right to the surface of the Earth, and we want to now calculate and consider what kind of forces act on this moon rock and what is the gravitational acceleration that this moon rock on the surface of the Earth is experiencing. So here we have the Earth. Earth has one Earth radius, and it has an Earth mass. And our moon rock has the mass m. And we know from this exercise here already that, of course, this gravitational force is acting on our moon rock as well. That hasn't changed. What we are now considering in addition is that this moon rock is also experiencing a gravitational acceleration due to this force, and that goes inward as well. So it is experiencing an mg. And we know that that is the same as the magnitude of this force here. So we can equate that with g, and then we have the Earth mass and the mass of the moon rock times the distance squared, so an Earth radius squared. And from that, we already see that we can cancel out the small m's of the moon rock, and we get to g here. So we can calculate the gravitational acceleration, which is capital G Earth mass over Earth radius squared. So if we have this kind of information, we can determine the gravitational acceleration, and of course it will change depending on which object we are considering. It would be different if we plug in the solar mass and the solar radius, or the moon mass and the moon radius if we consider an astronaut standing here on the moon's surface. Now let's put some numbers into this equation. So we have G is capital G, that's the gravitational constant. We have 6.67, 10 to the 11, and then we have Newton and 1 over kilogram squared, and mass squared, times the Earth mass, 5.97, 10 to the 24 kilograms, and then we have to divide this over through the Earth radius, 6.37, 10 to the 6, and we have to square that, and we have to square the meters. If we calculate this, we get to 9.81 meter per second squared, and surely you have seen this number before. this number can either be calculated if you know capital G, the gravitational constant, or you can determine the gravitational acceleration through an experiment, and together with the Earth mass and the Earth radius, you can actually calculate the gravitational constant there.